Good morning, everyone. Please come in from the atrium area into the plenary room. We're getting ready to get started. And good morning to our virtual attendees. Is that Molly we have on the line today?
No, it's Kelsey today.
Good morning, Kelsey. Thank you very much. Okay, we're going to launch into day 3. We are excited to hear about all of the networking that's going on, the connections that are being made with regard to learning about individuals who are doing research, the practitioners, learning about extension service connections to energy interests. I can't believe the real links that are being made at this particular workshop. We hope that they continue well beyond today. And we're going to continue to work on looking both at what we're doing today, as well as starting to look forward today. So this session 6, is Emerging Flash Drought Science. And our moderator this morning is Ron Leeper. And Ron is a climate scientist at the Cooperative Institute for Satellite Earth System Studies, CSIS? Did I get CSIS? Got it. At both North Carolina State University and the National Centers for Environmental Information. His work is exploring the intersections of climate and hydrological extremes. And Ron is also a member of the NIDIS Flash Drought Technical Working Group. Thank you for moderating this morning, Ronnie.
All right. Well, good morning, everyone. I may be a bit biased, but this is kind of a really exciting topic, emerging flash drought. Anytime I start a new project, that's where I get most of my energy. Like, oh, what's all the new things we could do? So as you think about all the connections you had and some of the new tools you learned about the Tools Cafe, as we integrate this, we got a really great discussion at the end looking at emerging research, and not just research, but also practitioner use of flash drought. So to kind of help get the juices flowing. And as you think about that, we got a great list of presentations. The first one's going to be Jeff Basara, and he's going to be talking about a framework of flash drought development and progression. Comes to us from the University of Oklahoma. He's an executive associate director of hydrology and water security program. He's also an associate professor there at a joint appointment between the School of Meteorology and the School of Civil Engineering and Environmental Science. I'll let you take it over.
All those titles mean that I have multiple jobs and one paycheck, and it's not enough. It's not enough. It's a pleasure to be here this morning, especially seeing some familiar faces as well as some new faces concerning this topic of flash drought. And even this morning thinking, I don't see Jason Otkin in here. Where'd he go? But he's outside, drag him in because it was about, I don't know, 10, maybe even 15 years ago now that he asked me a question, a very simple question, living in the Southern Great Plains, living in Oklahoma, now there for 28 years. Back then, he asked, have you seen any of these types of events that you might call a flash drought? And I said, I think I have. And that started now a long trek on our end of working together and then working with so many others on really trying to tackle this concept of what is flash drought, how can we observe flash drought, how can we find flash droughts in past climate sets and climate data sets, what are the drivers of flash droughts, what create them, what don't create them as well. What are the impacts of those? What's the predictability of flash droughts? All these questions that sort of arose out of just some simple discussions. And that leads to this particular point here. I'm not going to call it really emerging science because it's really continuing science and trying to understand the dynamics and thinking about flash drought from a conceptual framework and maybe sparking some new ideas about how we tackle this issue as we move forward. So just some acknowledgements, of course, and none of this work is done in a vacuum. Jordan Christian's my co-author specifically on this, but many have contributed to this work over the years. And one thing that is true is because of the impacts of flash drought, many agencies have supported the work over the years. So just want to throw out some appreciation for them. But again, I'm not gonna run through this. We all know these types of things, right? What is flash drought? And it really hit me personally close to home in 2012. I was working with an ecologist. We had a flux tower up in north central Oklahoma. An ecologist was he and I had been starting to work together on a number of things. And he asked me, do we have any cameras? Let's put some cameras on flux towers. And I said, really? We're going to put cameras on flux towers to watch the grass grow. And we put this camera on that flux tower in late May of 2012. And on July 1st of 2012 in north central Oklahoma, it snapped this picture. And then a month later, that's what it looked like. As flash drought occurred in the region and the soils and the vegetation were rapidly desiccated. And then my response to that was, we need cameras everywhere, right? Let's get the cameras out. Let's get them everywhere. We can observe these types of features. And these images actually made its way into that BAMS article that Jason led in 2018. But I also think we need to discuss drivers. And we talk a lot about flash drought. We talk a lot about how to observe it, know all those aspects of flash drought. But I want to make a real important point that flash drought is still drought. It is still drought. By definition, it is on its first order a precipitation deficit. We can't forget that. But obviously a hostile atmosphere, quick drying conditions. Joel a couple of years ago put together, many have put metrics out to try and observe flash droughts and detect them. And the other point I would like to make is one of the challenges of flash drought is it's a weather and a climate issue, but it's also at that interface between weather and climate and the subseasonal to seasonal, which is actually from a science standpoint and predictability standpoint, places where we have limited information and limited predictability and skill, which makes addressing issues like flash drought pretty difficult. Now, I'm a professor, so I like to throw out hypotheticals. If you've seen this before, do not spoil the answer. But I've got two time series of precipitation accumulation for stations in the Southern Great Plains. The one on the left is accumulating. I don't know, do I have a laser pointer here? I guess not. But the one on the left has a precipitation accumulation. I haven't put the numbers on here, right? Because that would maybe spoil the fun a little bit. But there's two precipitation accumulations that are going on here. And whenever it flatlines like that, that's a period of no accumulation of precipitation. And the question is both of these had a 10% period of precipitation or less than 10% of rainfall that occurred from July 1st to August 1st in the Southern Great Plains. And if you live in the region, that's usually not a good thing. So which of these two cases, if any, are a flash drought? Right? If flash drought is on first order a precipitation deficit, can you determine that just by looking at these? Well, I won't spoil it. I'll spoil the fun. It's a trick question because it's the same site in two different years. It had the same window of time where it had a precipitation deficit, but in the first year, in 2019, the black line, preceding that was an exceptional amount of precipitation. And the second one was right at about normal, and then it really tailed off. It was this last summer. Same site. And what we found, obviously, is that when we look, the one on the left really, there was some, by the end of that period, there was some abnormally dry that was showing up in some areas. And on the right, it definitely had cascaded into flash drought during that window of time. And we actually verified this using, the Caesar methodology and other methodologies. The one on the left was definitely not a flash drought, and the one on the right was. Same type of precipitation deficit, different endpoints, partially because of where the environment began in the first place. And so that gets to this framework that I wanted to discuss. And so let's just kind of think of this from a hypothetical standpoint. On the left is this, and what I'm calling here, this black line is calling the environmental pathway. Basically, that's the state of the environment at any particular point. By the environment, I'm talking soils, vegetation, atmospheric conditions, the entire state, the water resources of the environment. And you could have a saturated surface all the way on the left side of that, an unsaturated surface, a desiccated surface all the way on the right side of that. And so when we think about drought, you might start over here on the left-hand side, and then eventually, slowly, you can eventually transition all the way over to a desiccated surface. And this happens all the time from a drought standpoint. We see the environment move from a relatively well-watered condition to an unwatered condition. And so that's kind of the concept of an environmental pathway. And so in long-term drought, this might slowly evolve with time, get a little rainfall, might moderate it back along that environmental pathway. We typically see the environment kind of going back and forth in response to essentially precipitation and drought-related impacts. Now, this is also a case where there's maybe limited or no coupling between the land surface and the atmosphere. But what happens when we actually do see something like that? And what does it look like when we see something like flash drought? So I've changed the diagram a little bit here, and you'll see that the environmental pathway is curved, and there's a reason for that. And I put this thing called a soil moisture hill in here, and I'll try to explain that as I go along. But the terrestrial surface basically has its pathway back and forth in terms of, and it's often modulated by soil moisture, how much water is actually in the soil. And it supports vegetation, it supports a lot of the evaporative fluxes and the sensible fluxes as well, and the radiation budget. But on top of that is the atmosphere, right? And the atmosphere exerts essentially a pull for water. Call it evaporative demand, call it a hostile atmosphere if you want to, but the atmosphere is constantly exerting. It's drier than the soil surface. Evaporation is almost always happening. And in a coupled environment, these two are really working together, right? So what's also important to think about this is on the left-hand side, you actually have a negative feedback, because if it's well watered, and even if there's evaporative demand, evaporation is a cooling process, and it also moistens the atmosphere. So it actually works against drying. It's actually a negative feedback against rapidly drying a land surface state, because it's moistening the atmosphere, which decreases the evaporative demand. It's also cooling the atmosphere, which actually decreases the evaporative demand. So for a window of time, depending on where you are on that environmental pathway, on the left-hand side, it actually could be a negative feedback that would keep you from going to something like flash drought. Now, if you get over the hill, so to speak, and I'm over the hill now, so I'm on the downslope, but you end up with that positive feedback. So now evaporation ETs actually decrease. There's not as much water vapor going to the atmosphere. It actually transitions to a warming environment, which actually creates more low-level turbulence that can actually mix the boundary layer deeper. We get an increased boundary layer development, more drier that's actually entrained into the atmosphere. We increase our vapor pressure deficit. If you want to think about this from another standpoint, why I even used a curve here is, if you know what the Bedico curves are, there's a relationship between evaporation, precipitation, and potential evaporation. And on the left-hand side, this would be that point where it's energy limited. And on the right-hand side, this would be a place where it's water limited. What's interesting is what happens, right? When we talk about progression of flash drought, how does it move from one state to another? So let's go back to our examples, or in this case, you see the environment can move back and forth. And by the way, it can move back. It could be all the way over in that desiccated side, move back with a little bit of precip, right? Or cooling of the evaporative demand, maybe just cloud cover, more humid environment. In our cases, what I wanted to show here, by the way, I forgot I put this slide in here, but when we look at the atmosphere, oftentimes in flash drought, we only consider the land surface state, but we're not considering the atmospheric processes that are going on. And so part of this is also bringing in and starting to think about boundary layer processes and how they impact flash drought development. In these two cases, the case on the left, that was actually had a much lower boundary layer depth and a much more humid atmosphere than the one on the right. And so we can actually see the reflection of these flash drought cases showing up in the boundary layer and in the overall atmosphere. So in the case of case one, what we actually had was something that was very saturated, and it kind of got to this point, just over the hill, but it never really got into that positive feedback process, which could drive it further along. So where it started was really important in terms of after a month where it was at. And then it got modulated and it went back to some other state, and it never quite got to flash drought. In the other case, we actually saw case two actually probably started much closer to that tipping point. Between the negative feedback and the positive feedback. And what ended up happening is we know that it cascaded rapidly into flash drought conditions, desiccated land surface, and really significant impacts this last summer across large portions of the Southern Great Plains. So a part of this is starting to think about flash drought from where they begin as where they end, and whether or not they get there. By the way, if we could think about this from environmental pathway standpoint from a couple of different perspectives. How we even observe flash drought. Most of the time when we observe flash drought, we're all the way on the right-hand side. You haven't really considered how it got there in the first place. The other thing is there are probably many cases where the environment was trending towards flash drought and never got there. Null cases. We don't, as a scientific community, study null cases very well. And to date, I haven't seen anybody present a paper or an analysis on a null case of flash drought, where the environment is trending there, but didn't quite get there, and why. These are things in the emerging science that we do need to do. And we need to consider sort of the overall bigger picture of what's happening in these processes. So some thoughts on progression. Not all droughts are the same. You'll hear me say that over and over again. I even got it published in a paper because I think it's an important statement to make, which means that the impacts are not all the same, which means that the way that they got there was not always the same. And we have to kind of think about these. Now we can categorize them somewhat, but we still need to think about that not all droughts are the same. These tipping points are probably really important. How we quantify them is going to be different for each environmental set of ecosystem and environmental conditions, vegetation. That's why we see differences in how flash drought progresses in many areas. And so we kind of need to think about that in different ways, perhaps. You can actually go back, and when there's moderation, vegetation, ET, density of vegetation is going to be really important in how that environment progresses from one side to the other. And then of course this coupling really is really a big deal as well. And then I think we really do, from an emerging science standpoint, need to really address this tipping point issue when we go from that negative feedback to the positive feedback, because I think oftentimes we start seeing some aspects of flash drought. We also start seeing some impacts, but where are we in that spectrum, right? Are we past the tipping point? Are we going to see that rapid acceleration, or is the environment fighting against flash drought development? There was a recent paper, I know at least one of the authors is in the room on this one, and is flash drought onset becoming more prevalent in a changing climate? I know Jordan presented a little bit of his work the other day on this. And we are starting to see that maybe in the future globally that we're going to see more of these types of events in more and more locations. And so the question I ask is that, from the framework standpoint that I just presented, is that because the ambient environmental state is being pushed closer to that tipping point? It's getting more hostile to the atmospheric environment. Soil moisture is more relatively dry. The atmosphere is warmer. Are we just putting the environment closer to that tipping point so that it doesn't take as much of a nudge to drive everything into flash drought, right? And I think that's another thing to really kind of consider when we think about these tipping points. And then finally, it is, we heard it yesterday, we saw it up on the screen. We need a hero in order to help lead us in these endeavors and continue to lead us in these endeavors. I think on the screen yesterday, it said we needed Jason Ocken. Today is May the 4th. If we need a hero that's going to help us to get past this, then maybe, just maybe, we can rely on Dr. Jason Ocken, because on May the 4th, he might just be our only hope. So with that, questions? Jason, May the 4th be with you.
So we have a couple minutes for questions if anyone wants to come to the microphone in the room. And
I can get this to work. Oh, really? Okay. Well, I won't embarrass Jason any further. Great talk, Jeff. I was already primed for it because I've seen it before. You had made mention that some of these flash droughts don't lead to impacts because you were doing this within a physical basis,
Sure.
Which tends to be how I approach problems because of my background. That kind of differs from where we were the other day. Like, well, we need to have impacts for us to actually care. So what say you? Do we need to understand the physics and just focus on that? Or do we say, this isn't even worth our while because there weren't impacts?
No, so that's a great question, Andy. Thanks for bringing that up. We had a little bit of this discussion in our working group yesterday afternoon, because if we really look at how most of the science has actually progressed for flash drought, it's been driven by the desire to understand the impacts. The impacts are significant and severe in many cases with flash drought. And when from a science standpoint, the many individuals in this room who have contributed to the science of flash drought, and then beyond this room even, have really done so, I think, with the mindset that because of the impacts, this is a really important issue. I still completely agree with that. In fact, you can ask Jason, he and I have had this discussion many times of, drought has impacts, and that's where we end up in many ways. I do think it's worthwhile though, looking at these cases, especially that where we see the environment evolving, but it doesn't actually produce the impacts, right? Because I think that is helpful in understanding the whole big picture of the science of how flash drought and how these events even evolve. I've gotten a little more curious in cases that don't quite get there, because I think that there's some interest in this from the scientific side of the other side of this, because if we're ever really going to get the predictability, we need to understand the drivers that cause flash droughts to get there and not get there. But I don't for a second think that we should ever forget of the impacts that drive these events, because to be quite honest, that's where the end point is in terms of the research and science. And that's where our biggest impact as scientists is going to be.
Thank you. And just kind of a terse comment. Now we're going to have a rash of papers that talk about the failed flash drought, say of 2023.
Maybe
go.
2019. Anybody who wants to work on 2019, we'll work on that one. So in the Southern Great Plains. But,
Becky, yeah.
Becky Bollinger with the Colorado Climate Center. I really like your conceptual framework, and I'm thinking about it from the perspective of, in our tabletop exercise yesterday, we're the Western group, and the idea of, do we get flash droughts? And I was wondering what you might think of a conceptual framework for an area that is almost never in that energy limited side of the curve.
in terms of it's always has available water, or if it's not energy limited, it's always in a water surplus, or okay, you're water limited. Okay, so yeah, so that is also, yeah, I've had debates a little bit about, can you have a flash drought in a desert, right? Can you have rapid intensification of drought in a desert? One thing, so what I haven't described is the full nature of that. And if you ever go to my office, my whiteboard, I've got all these extra things on there, like time derivatives, right? How long does it take that curve? If you have really big atmospheric demand, actually it narrows it. The time to get from one side of that to the other might be less, because you have really severe atmospheric demand. Look at what happened. I think the Pacific Northwest case of 2021 is actually one of the best examples of what can happen in that type of environment. Maybe even not in the right place, but where the atmospheric demand was significantly off the chart. Everything happened in a really short framework, right? Between, it was already primed towards the tipping point. We saw that it was dry, and then boom, it dropped off the cliff. By the way, I believe that was a flash drought, and some of the analyses that we've done, but it's so fast. And it's shocking in an environment like that to see something like that happen, but it's because the atmospheric demand was so high. Now, when you get into more arid regions, I think that poses a bigger challenge, because you're always either at that tipping point or beyond, because on the environmental pathway, right? And so you can instantly cascade into something that's even more dry from a coupling standpoint. I think we still have a ways to go to really answer and address and deal with those types of questions. But I think maybe this will help us to think about how we do that in the future. So, thank you. All right, thanks.
Hello, we had a couple of quick questions from the virtual chat if we have time.
Yeah, well, I guess we can. Do you want to try to tackle those real quick? Are they pretty quick questions? Just one. We can do one.
Okay, one question. So very interesting study, thanks. How many the hill and the tipping point vary with region and season over the contiguous US? Past studies have shown that soil moisture based flash drought in the central and southeastern US during the warm season. How can we better understand the observed regional and seasonal variation of flash drought occurrence using this conceptual framework?
That sounds like one of my test exams where it's one question, but it's like 8 different parts. First of all, that environmental pathway is going to differ everywhere. And I think that this is one of the challenges that I'm struggling with and wrestling with myself, is how do you even define that? So we can nebulously define it, but then how do you quantify that and tackle that soil moisture hill? concept or the Bedico curve concept. I think that's where the answer is sort of hidden. But I think, yeah, when you go from one place, say the Southern Great Plains to the Southeast, to the Pacific Northwest, to the Northern Great Plains, to the Sahel of Africa, to the Indian subcontinent, to the interior portions of Australia and Southeast China, you're going to have different types of characteristics that define those in all those locations. And so actually that's part of the emerging science actually on our end, is being able to address that in a way. But I think, again, just kind of back to it, I think that there's some hidden gems in approaching it that way in terms of understanding the overall aspect of how these flash droughts evolve, especially when we start thinking about how the atmosphere works in tandem with that environmental pathway through the depth of the atmosphere. So I don't know if I entirely answered the question, but especially parts A, B, C, and D. So thank you.
Thank you.
All right, really interesting topic. So the next presentation is entitled Subseasonal Flash Drought Prediction and Skill, or Prediction Skill in the Contiguous United States by Kyle Lessinger. And he comes to us as a PhD student from Auburn University, and he's working toward improving climate resiliency through historical flash drought assessments, identifying predictability within subseasonal models, and utilizing deep learning to enhance our predictability. Yeah, please.
Good morning. Thank you for having me today. Let's see how we do this. So, how do I go backwards? All right. So I'm working under the advisement of Dr. D. Tien at Auburn University and collaborating with Dr. Hailan Wang with Climate Prediction Center. So I have a lot of slides, so I'm just going to jump right in. Here's a basic outline for my presentation, just going over an introduction of subseasonal models, looking at some of the data that I've used, my methodology, and a few results, preliminary results, and then conclusions. So some of the difficulties that come within subseasonal model predicting, so these are coupled models, usually between land, ocean, atmosphere, and sea ice. The difficulties arise with the different complex interactions that are occurring on varying timescales across the globe. So just a few with the more high frequency, like the MJ, I think the slide works. So with the MJO, that doesn't work too well. With INSO, which is a little low frequency variability, there's also interacting between the land atmosphere feedbacks on varying timescales. And so all of these conditions can create different weather and climate outcomes based on the current state of the atmosphere, land, or ocean. And so Dr. Becerra alluded to this just a moment ago with the predictability. The knowledge of the initial state is really important for understanding atmospheric predictability on short lead timescales. But then as we progress longer into these forecasts, then we're going to see that the land and ocean, these more slowly varying components, they do have in part some predictability, but we still need to better understand the areas where all of these are interacting at the same time to produce increased skill. So this would be related to those forecasts of opportunities, such as with the 2019 Southeast flash drought, where they noticed that the Indian Ocean dipole was influential in creating that Rossby wave. And so this also equates to overall forecast skill when we're looking at these atmospheric short-term leads. We have this high skill, but as we get longer leads into those forecasts, we have diminished skill. And this subseasonal range has been noticed to be a subseasonal or weather climate predictability gap. So looking back at the 2012 flash drought, so this was from a paper by DeAngelis et al., we can see based on the average of that in the right-hand box, this slideshow, there we go. The average of this central US region. So we have precipitation, temperature, vapor pressure deficit, root zone soil moisture, latent heat, and sensible heat. And so what I've noticed here is that with the beginning of the drought, so it really progressed heavily in July, but at the very beginning in May, we can see that there were some precipitation deficits right here at the bottom, but then the temperature was not anomalous, or it wasn't greatly anomalous. And we can see that root zone soil moisture, it did decrease a little bit, but the major impacts that occurred were occurring in July. And so just because we have these precipitation deficits definitely doesn't mean that we're going to enter a flash drought. The conditions need to be right and under varying scenarios. And so over here on the right, we can actually see the 200 millibar geopotential height. And so this is actually what enhanced the previous precipitation deficits, which we can see that there were additional precipitation deficits right here and enhanced the temperature and vapor pressure deficit anomalies. And then root zone soil moisture, it just dropped very low during this time, during this flash drought. And so when they were looking at these subseasonal models, specifically within sub-X, the most skillful model was the GEOS GMAO model. And so we can see that based on these Hofmuller plots, that it slightly captured the anomalies that were going with temperature and precipitation and soil moisture, but it definitely didn't capture the intensity of those anomalies. And this is definitely related to the initialized conditions from soil moisture, which do play a large influential role in future predictability, as well as the unable to capture that propagation of the Rossby wave. And so these limited the predictability for these models. Additionally, Osmond et al. Used a k-means clustering to look at the antecedent conditions prior to soil moisture volatility index or soil moisture flash droughts. And so the two key variables that they identified that were pretty much always either anomalously low or anomalously high were root zone soil moisture and potential evapotranspiration. And so using this knowledge, we were able to confidently use specifically soil moisture and reference ET as our indicators for flash drought assessments. So my main objectives were to look at the prediction skill of soil moisture and evaporative demand anomalies at leads 3 and 4 within sub-X models. And so we looked at them between 2000 and 2019, and then assess the utility of a flash drought index and actually predicting these rapid changes that were occurring in soil moisture. So sub-X does have 7 models that could be used, but after sorting through them and seeing what variables were actually available, so we decided, and I'm only really going to present on 2 of these models today, but many of these models, they may not be necessarily appropriate for flash drought analysis. So using EMC GEFS V12, so this is an updated version of their GEFS that they initially had within their sub-X database. And then we're also looking at GMAO GEOS model. And so they do have a varying number of ensemble members, with GEOS having, or GEFS having the highest number of ensemble members at 11. And so for verification data sets, we wanted to explore what it looks like for forecast skill if we're using different reanalysis data sets, because previous research has also shown that each reanalysis, it does capture some part of the land and atmosphere state, but due to differing parameterizations that are involved with each of these models, they can have some differences. And so all the variables I selected related to flash drought, precipitation, temperature, wind speed, radiation, and soil moisture. And so for this, we only use the GEFS model because these actually have soil moisture partitioned into the 0 to 100 centimeter range, whereas most of the other sub-X models, they don't have this partition range exactly for these depths. So we looked at the Penman-Monteith FAO 56 method. We look for reference ET, and then for anomalies, we remove the seasonal mean from 42 days. And for us, we use the soil moisture percentile drop as our flash drought index. So we divided our regions based on the NCA LDOS. They recently came out with this new gridded mask. And so these are the 6 regions that we use with so within the West, Midwest, Western High Plains. So that would be Colorado and Nevada. No, not Nevada. Now I forget the name of the state. Yeah, Wyoming. I'm sorry. And so with the High Plains, Southeast and Northeast. Thank you all. All right. So for reference ET, so we were looking at GMAO and the EMC model. So, and these are for the 6 different regions. So we have the West region right here, the Midwest region, the High Plains, the South, Southeast, and the Northeast. So in general, we can see that week 1 anomalies for reference ET, they're fairly high. So they can range from 0.8 to 0.6 anomaly correlation coefficient. And so any values above this 0.5 range, they're generally indicate skill, because this 0.5 range is kind of where the climatological errors are equal to it's just simply using the mean of the forecast would be just as skillful. So, so for weeks 1, and we can see these leads right here down at the bottom. So after lead 2, we do see the typical drop in skill in which, so we're losing all that predictability from our initial conditions. And then slowly during weeks 3 and 4, we've pretty much lost all skill. So they range anywhere from 0.2 to 0.4 anomaly correlation coefficient. And so both models are very similar with their results. And this is, I'm sorry, and this was only, we did compare both, as I mentioned, MERA and GEFS reanalysis, but for the sake of keeping this short, I'm only presenting from generally one model. So for root zone soil moisture, this one was much more variable when compared with different models. So these are our reanalysis data sets that we were using. And so we only use that GEFS V12 reforecast. So if we're looking at the skill between different regions, we can definitely see that even at week 1, we do have a large degree of variance between models. And it was highest with GEFS V12 when compared to its own reforecast. And so we can have up to 0.9 anomaly correlation coefficient at week 1, which is very, very high. And this is kind of what we would expect. Week 1 forecasts it's not much deviation from our initial conditions. And as we progress later on into the forecast, so for many of the models in regions, we can actually see that it still retains above 0.5, which is good. But then the question is this just due to autocorrelation? And does this autocorrelation actually impact predictability of extreme events? So with the soil moisture percentile drop index, we assessed over all regions and seasons. We wanted to look at the true positive and false positive rates. And so the big picture right here, and I'll just summarize it, is that for true positive rates, it's still fairly low. So anywhere from 5 to 25% of the time, we're able to accurately predict those true cases in which flash drought occurred. But then there's also anywhere from a 1 to 10% chance that we're falsely predicting soil moisture flash drought when it did not occur. And so the Northeast was actually the most skillful for this, for specifically the spring season. And so this divided by the season. So overall, we can't say that we can use this specifically for all flash drought. So then we wanted to analyze what about the major case studies that have been previously talked about. So for our methodology, because the reanalysis and the reforecast are in different formats as far as date time, so we just reformatted the reanalysis to be the exact same lead time format. So every 35 days, we're relooking at the same days between forecast and reanalysis. And so for this also, we want to say that we do look at it as it goes further into the future, but this analysis isn't for looking at the previous date. So this is a new assessment of a drop from above the 40th to below the 20th percentile for every forecast. So looking at the 2012, we can see that, yes, we have a decently high true positive occurrence right here in the central United States. So this was in May. And so this was prior in that very first image that I showed. So we did see those precipitation anomalies, and we did see some soil moisture anomalies that were progressing. And we do capture these, but generally for geopotential height at 500 millibars, it doesn't capture the intensity nor the location of it. And so this has kind of previously been shown for the other models, specifically GMAO, that it didn't capture the progression of that Rossby wave train. And also the precipitation anomalies, these are actually better forecasted, it looks like, at lead 3 than they generally are with all of our other results. But those lead 3 and lead 4 precipitation forecasts are still not well represented. So then as we progress into week 4, so we do continue the droughts if they do stay below the 20th percentile, but then we start to see a large true false positive rates that are occurring. And this would be related to also the geopotential height location, as well as the placement of ETO anomalies. So, and if we were looking at the US Drought Monitor, we can see, yes, we did have some rapid changes that were occurring. Whether or not it was a 2-category degradation is generally we're not in those specific areas, but GEFS did capture some of those anomalies. And so this was actually 3 weeks later. I couldn't include every image that was happening between May and July, but just some of the highlights is that, and these are false negative. Anywhere where it's a blue, it means that the forecast missed the flash drought occurrence. So we know that it kind of started, if you look in some other papers where it kind of started more in the eastern central US and then it progressed west. So we can see there's kind of a large number of, it's just kind of hit or miss with these forecasts. And so also it's mainly related to, you can see the geopotential heights kind of misrepresented, especially at week 4, we don't get the same intensity. And then soil moisture is generally, there's a dry bias that occurs later on in these forecasts, which the results I didn't show, but for these forecasts, yes, as lead time increases, it tends to have a much more dry model bias. So, and then finally, we're getting to where we're actually hit in the center of the country. And so these places are already in drought, but as I mentioned before, this is only capturing those rapid decreases. It's not really looking at the historical, is it already in drought, flash drought? We just want to see, can this capture rapid decreases in soil moisture? And so specifically, you know, in the central United States, this is kind of where it was starting to get really bad with soil moisture. And for the most part, we do see a lot of false positives, and it does capture some of them within the center. But as we can see with these, and this is also kind of a rounding artifact because it was trying to add more values to here and I couldn't fit them in the thing. So, but in general, these reforecasts are they produce a lot higher soil moisture anomalies than our reanalysis did. But the reanalysis did, even though this doesn't seem very intense as our soil moisture, it did capture it with being in flash drought based on that index. And then finally, I just want to look at the 2017 flash drought. And so this one was in the northern high plains. And so for looking at those dates, we can see that the sub-X model completely missed all of those occurrences. But then by week 4, it was able to capture some over in Minnesota, but it wasn't able to, in Wisconsin. I'm bad with geography today. I'm sorry. And those are potentially related to those precipitation anomalies, and it didn't capture ETO. And so it seems a lot like the ETO, you know, and geopotential height, they're following one another, because when those height anomalies are high, then we're having dry descending air, which is increasing the vapor pressure deficit. And so this will increase ETO. And so as we progress further, we can see that it's still missing any new drops in soil moisture. But then one noticeable thing is that in the southeast, it's classified by week 4 that this area is in large area of flash drought. And so we can actually see that by week 3, the precipitation is in the reanalysis. So it occurred in observations, but it was completely missed by the reforecast. And so what this means is that by week 4, since there still was no added precipitation, it was actually classifying this area in flash drought, mainly because of the precipitation that it missed. And then one notable thing is that we do sometimes see areas where it's just extremely high. So this is still the 2017 flash drought from June, initialized and looking into July. And so from the Western US, so we can see that there's a lot of areas where, yes, it was correctly identified as positive. There's a couple areas of false negative, but, and then as we go to League 4, we can see that, yes, it correctly classified these areas. And so overall with these case studies, I mean, we can see that sometimes it has a good signal and it's in a very large area, but then other times that there's this very big false positive. And so that would impact how we can actually use these forecasts in their current state to increase our confidence in what these results are. And so overall, we can see that for soil moisture, we do have high predictability at leads 3 and 4, and this has kind of been alluded to in a Otkin paper when they were looking at autocorrelation, and how high autocorrelation implies generally low predictability for these extreme conditions. So we also have lower skill for ETO, for reference evaporative demand, and so this is going to impact how these coupled models are able to forecast the soil moisture flash drought. The low true positive rates do not necessarily indicate that we can currently use them in operational settings as a good means of actually saying, yes, we believe that the flash drought is going to occur in this region. Case studies show moderate classification in some regions, but there's still a lot of work that needs to be done in representing long lead forecasts of precipitation, geopotential height, and evaporative demand. And rapid decrease in soil moisture do not always imply that drought-related impacts exist. And so this has been alluded to before in this conference, is that just because we have a drop in soil moisture, it's really hard to say whether the impacts were on land. And so it would be optimal if there could be a model that was forecasting vegetation that was also included within this, so that we could see that if anything, but SubX doesn't currently have any of those capabilities. And I welcome any questions or feedback. Thank you.
So in order to stay on time, we can maybe, do we want to entertain one question? Yeah, so if anyone wants to come to the mic, or if we have a question from the virtual audience. All right, well, hearing none, thank you very much, Kyle. Okay. So the next talk is going to come from Kashan Mohammadi, and they're going to be assessing the performance of subseasonal solar-induced fluorescence trajectory, that's a mouthful, as an early warning system for flash droughts in the U.S. regions and ecosystems. He comes to us as a fourth-year PhD student from the Department of Civil Engineering, Civil Environmental Engineering at the University of Connecticut.
Hi, everyone. Thank you very much. I'm a fourth-year PhD student under supervision of Professor Pauline Bong. Here in these sessions, we talk a lot about the flash drought impact on ecosystem, its stress on ecosystem, its impact on grassland and croplands, and it has an increasing risk of wildfire. So the main problem of the flash drought is because of its rapid onset and intensification. It creates challenges for drought early warning and monitoring, and that is what is the main cause of this flash droughts. So our main motivation when we entered to this area was that the hydrometeorological data that needed for conventional drought monitoring index were mostly sparse and poor quality in developing regions. And so we felt that if we go to using satellite data, it might be more beneficial. And a flash drought's impact on vegetation mostly can remotely sense it by satellite at global coverage. Solar-induced fluorescence SIF is a proxy of the plant's photosynthesis that is provided by various of satellites. So that's where we went to use these variables. And but as we went more through, we saw that the performance of vegetation-based flash drought metrics can be varied over different ecosystems and over regions with different vegetation type. So we also use VPD and soil moisture because we want to assess the performance of the metrics that we are going to introduce, and we use those variables because they are sensitive indicators of drought, and they could be good metrics to assess the performance of vegetation-based flash drought. So as I mentioned, the objective is develop a flash drought early warning using satellite-based SIF dataset and assess its performance over multiple regions and ecosystems. So these are the data sets that I used. For SIF, I used both from GOMI2 satellites and GOSIF data sets. They are provided at 8-day time resolution and at 0.05 degree resolutions that is also suitable for people that just wanted to do field scale analysis, and it can be suitable for them too. The flash drought, our main approach is to detect that rapid onset and intensification. So for the SIF, we look at to detect that its rapid change by using this RCI method and develop the SIF RCI metric. And for the assess this metric, we look at the plant water availability by looking at soil water deficit index and the change in that index to detect that rapid onset and intensification. So this is the RCI. So this is basically based on the standard anomalies of change of that variable and accumulation of that. So for example, the positive RCIs means a faster than normal increase or slower than normal decrease, or negative RCI means faster than normal decrease or slower than normal increase. This is for a stability I that basically it's a representations of a plant water availability. So the positive value means there is a wet condition and negative value means drought condition. For example, -10 means that the soil moisture reached to that wilting point that as an indicator of very dry condition. So for a stability I here, I only used root zone soil moisture because surface soil moisture has a lot of variability and it wasn't really suitable for detecting because we want to look at the change of this variable. It wasn't really suitable for that purpose. That's why we look at this root zone soil moisture. So for the result, at the first, I'm looking at two famous flash drought over US. So this is the 2012 flash drought, and based on USDM, it was detected at nearly July, end of July, but using SIF RCI, we could detect it in middle of May. And by looking at the time series, we can see that the SIF RCI and stability I that I developed based on the routine soil moisture, they start that decreasing trend almost at the same time. However, SIF RCI reached to -2 on May, which is a very high value for SIF RCI, but stability I continues its decreasing trend until the July and reached to -6, which -6 is a representation is a strong drought. So this is why that by SIF RCI we could detect that signals in May, but for example using USDM or stability I, although they had those decreasing trend, but it didn't give us any specific signal. And USDM also that the decreasing trend is start with a lag compared to the other variables. And also we could see that VPD also is showing us the VPD is a standard anomaly. So it is showing us the positive value in that regions, in that location. So it also has its own impact. This is 2017. For 2017, USDM, it gave us the signals in early July. With SIF RCI, we could detect the signals in early June or end of May here. And so the lag time here, it was a little decrease compared to the USDM. And we could see that, again, the same thing happened, that decreasing trend between the root zone soil moisture and SIF RCI, they start at the same time, but SIF RCI could give us better signals because it reached to its maximum negative value much way faster than other variables. And you can see that also USDM had this increasing trend, but it took it time to reach to that level that it gave us really signals of the drought. And you can see the very high correlation maybe of VPD and SIF RCI in that extreme event that happened here. So I'm looking at 2 or 3 other flash drought here. This is for 2003. And we could see that here SIF RCI gave us less robust signals here. The reason here because in here I use GoSIF, not GoMe2, because GoMe2 was only available from 2007 to 2018. GoSIF was available from 2000 to 2020. But still a -1. This is still considered as a robust signals if it continues for multiple time steps. And we could see that again, such as other the decreasing trend start with the stability I, but it gave us better signals and have high response to the VPD here. For 2007, USDM couldn't really catch that drought in the locations that I'm showing you. If we go to the west a little bit, the USDM also is showing that decreasing trend and the drought signals. But in that locations that I'm presenting here, it didn't really took it. However, both CIF-RCI, SWDI, and VPD, they are showing signals of the flash drought, but USDM couldn't really show it in this location, and CIF-RCI also could detect the drought with the good enough lag time here. For 2019, it's a place that CIF-RCI couldn't really detect it, although this is a very wet location. So we had that very rapid increasing of root zone soil moisture, but at its worst time, based on this index, it was reached to the mild drought. And VPD has very high anomaly, but CIF-RCI couldn't really detect it because CIF-RCI, as I said, it is a proxy of vegetation photosynthesis. And in this location, because mostly forest and with the very deep roots there, they weren't really, they didn't get any most damage from that flash drought that happened in that location. So at the end, I also wanted to look at free root zone soil map, root zone soil data set, and I developed the SWDI based on them. What was interesting was that the variability of this data, of all of these data sets, were very similar. However, the range of this variability in some cases was different. And this, for example, SWDI is very sensible to the field capacity and filtering point that we want to use. And if you look at SMAP, GLIM, and ERA5 and other models, you see that they're using different field capacity and filtering point. So here I use only one field capacity and filtering point and apply it to all of these data sets. That's why you see some difference, but that's the problem that maybe is there. And also a SMAP level 4, I think that the value itself, if you look at their paper, you can see that it's underestimating the root zone soil moisture compared to the observation value. So the conclusion here that the CIF-RCI performance was very good over grassland and croplands. And SWDI is also very powerful proxy. You could see that it has a very rapid change. However, it was the problem. I mean, it's based on our decision that okay, this threshold is a signal for us, and we don't need to be more continue to the negative value there. And the soil moisture-based flash drought is subject to a lot of uncertainties because of soil parameters, because they not only depend on the type of the soils, and also the different models provide different estimations for them. Thank you very much.
All right, so we have time for some questions in the room, if anyone's got some. So one of the questions I had, you were looking at standardizing the soil moisture based on the soil properties. If you kind of created baselines for the different models in that last graph and looked at how they change from that climatological kind of baseline, do you think you would see better correlations between the two, where you're not trying to, because you used one wilting point and fill capacity for them all. And so you made a choice there, but if you allow each one to vary within its own kind of climatological range, do you think you would have seen something?
I think because I wanted to look at the plant water availability, not the soil moisture itself. That's what I use that index. But yeah, that could be a choice for me to continue with that. And for the SWDI itself, we saw some very, good performance in the case of flash drought. The things that I was mentioned, that, for example, CIF-RCI, it reached to that critical value much more sooner than other signals, because the decreasing trend was there, but in the thresholds that those other values, the other metrics gave us the signals, it wasn't there because they continues to the decreasing trend, but CFRCI reached there and then give us the signals.
We have one in the room.
For the presentation.
Thank you.
Okay. So I have a question regarding the SIF. So for the 2017 case study, for example, what does it mean for the SIF being dropping and then rising back again?
Okay, when CFRCI showing the negative value and it is decreasing, CFRCI is a representation of rapid change of the standards anomaly of change of that variable. So the negative value, especially in the growing season, it means probably we are looking at faster than normal decrease there. So that's what is representing then. And when it became more negative, it means we have faster than normal decrease compared to its long-term mean of that change for that time step. So that's what is meant.
The rising part doesn't mean it's increasing.
And maybe one of the things that I forgot to mention here for 2017, we saw that positive value in August, and this is also we could consider them as a signals of flash recovery. Because we saw that SWDI, the root surface moisture, kind of start to decreasing USDM showing some recovery signals. So that means the faster than normal increase for the SIF in that time period. So it is also considered as a flash recovery.
One quick question. So for the soil moisture comparison between the different data sets, is it all defining the root zone the same depth? Because
all of them were from first 1 meter.
Just because it shows like almost like a constant difference between the data sets, but same pattern.
I said I didn't hear.
Almost like the same pattern if you look at the time series, but it's like constant.
Yes, it has same pattern, but as I said, because it has different models, and the problem with this different models is that because they use different soil parameters, they probably get to the different estimations. We talked about it yesterday. I developed a flash drought hotspot based on different data sets, and one of them went toward the shows that those dry lands, dry regions as a regions that are vulnerable to flash droughts, and other will move toward those Midwest and wetter regions. So that's some maybe a problem using different models for soil moisture.
Thank you.
Thank you.
Hi, we have a couple questions in the virtual chat if we have time for at least one of them. The question is, I'm curious to know how vegetation index can be utilized as early warning compared with other variables such as precipitation, evaporative demand, or soil moisture. Doesn't SIF show more impacts?
Well, SIF is the impacts that plants get from them. So they are so it can maybe it's a summarize of all the impacts that can cause from them, but it wasn't really detectable at this moment. For example, in 2012, if you look, you see that okay, we have, I believe, lower than normal precipitation, maybe normal temperature there, but and in soil moisture, I didn't look at that, but soil moisture probably decreased a little bit prior to that time, but none of them really gave us any signals about that flash drought happens. For example, you couldn't see it in the USDM, but vegetations, they could detect this signals because they are under influence of those anomalies that could happen. That's why we felt that if we look at the vegetation health and photosynthesis itself, it could give us, and it gave us the better lead time prior to that events that could happen and before that wilting condition come to.
Thank you.
Okay. Thank you very much.
All right, so for our final presentation this morning, it comes from Emma Scott. She's a research associate at North Carolina Institute for Climate Studies, and she's going to be talking about flash drought prediction and connections to the Madden-Julian Oscillation. Take it away. Emma.
Hi, so today, as Ronnie mentioned, and thank you for the introduction, we're going to be talking about teleconnections and how we might be able to use these to predict rapid drought change. So we know that we have inter and intra-annual modes of variability like the MJO and INSO, and we know that these influence regional precipitation patterns, both on their own and in concert with each other. So we have an example here at the bottom, and this is just taken from a climate.gov infographic. And it shows you've got rainfall peaks during specific phases of INSO, and then rainfall peaks during specific phases of the MJO. And when these line up together, you can get extreme wet events. And when the troughs line up together, you can get extreme dry events that could lead to rapid drought development or intensification. And so we want to see if we can feed these into models to try and improve lead time in predicting these events. So the first step here is to identify the rapid drought change events in the historical data, and then using machine learning, create models that can identify the rapid drought changes. And in order to do that, we're inputting the drought monitor category, the latitude and longitude or position information, and the Madden-Julian oscillation and INSO. And then using all of that, once we've analyzed these events and created a model using the inputs, we want to then turn that into a predictive model using the same framework. So we start off by characterizing where flash drought occurred and where flash amelioration occurred. So we're defining flash drought here based on 3 category degradation in the US drought monitor over 5 weeks. And so flash amelioration here is just defined as the opposite of that. So a 3 category improvement over that same time frame. The rate of change for flash drought would be greater than 0.6, and the rate of change for flash amelioration would be less than negative 0.6. So we identified cases where we found that these events had occurred over the US, and the flash drought map appears on the left, and the flash amelioration map appears on the right. So we're seeing mostly events over the central US and into the southeast, with a relatively low count of events over this 2000 to 2021 period. And similar for flash amelioration with more of a bullseye over Texas. And you may be wondering, how are we going to use machine learning when we have a small number of cases, but we're treating each grid point separately. So then that helps us get the numbers that we need to train the model. So then we take those IDs of where rapid drought change occurred, and we align them with the MJO and INSO phase data on a weekly basis, and then divide that into 2 data sets. So we have a training data set that we're going to feed into the model initially in order to train the model. And then we also have a validation data set that we use to test that model's performance and say, can we use this on data that wasn't originally fed in there to see if it'll generalize as you go further out. And we also broke these data sets up into an equal number of flash drought, flash amelioration, or neither cases. And we do that in order to prevent sampling issues. So if we fed the data in the proportion in which it naturally occurred, then the model would be influenced to just predict the neither case, because usually you're not seeing either flash drought or flash amelioration. And it would best improve its score by just never predicting it. And we don't want that. So we have to take an equal number of cases from each category. So once we have the data ready, we run the models, and these are all supervised multi-label classification algorithms. So we tested out linear regression just as a benchmark, then a decision tree, and boosted decision tree, which just takes any residual error from the decision tree model and then feeds it back in to try and improve performance. Random forest model, which is just many of these decision trees, and then you compare between them to try and find the best one. And then there's a k-nearest neighbors approach as well that we had used. So we trained all 5 of these, and we performed cross-validation on these as well. And that consists of taking smaller subsets of your input data and running the model on that smaller subset, and then comparing between those. So when you do the cross-validation, you don't want to see one of those smaller subsets jumping out as much better performing, because that would mean that you were introducing outliers into the data that could strongly affect the model going forward. So we want those to look the same across all of the folds. And then you can also do hyperparameter tuning on this. So you can change the number of trees that go into a random forest model, or the time that you allow the model to run for. And all of that can be tuned in order to try and come up with the best model based on your data. So once those are created, we then run the models that were created from the training data set on our testing or validation data set, using the same inputs, but from that 2015 to 2021 period. We feed those into the models and then get a rapid drought change category. So then when we look at the performance across all of these, we're seeing precision and sensitivity scores around like 0.5 to 0.6 for some of the better performing models. The boosted tree and random forest both did fairly well, but all of the tree-based models are kind of similar. And then the k-nearest neighbors was doing the best out of all of them. So there's still room for improvement here, because when we ran this on just the training data for the initial training and without running it on the testing data set, we had much higher sensitivity scores, closer to like 0.9. And that means that we're probably overfitting a little bit to our training data. And so there are things that we can do to improve that still. So then once we had these models set up and ready to go, we can then take this from an analysis-based approach to a prediction approach. So before we were just looking at the rate of change over the last 5 weeks. Now we're looking at over the next 5 weeks, will that rate of change meet our threshold? So for week 1 before, you might have identified a flash drought event because of the rate of change for that week or for the past 5 weeks. And then for the whether or not we'll see flash drought change in the future, you'd actually be predicting flash amelioration, because out at week 6, it would reach the correct rate of change for that. And so then when we change it to be a predictive model, we narrowed this down to just 2 of the models, the boosted tree and the k-nearest neighbors. And when we include all of the inputs, we're getting just about to slightly better than chance with precision and sensitivity scores. So somewhere around 0.6 for the precision, depending on which model you look at, and then about equal chances on sensitivity. And then as you take the MJO out, we actually didn't see much impact here. And then taking out the drought monitor category also reduced the score or the current status that we were in. So the current US drought monitor category had the highest importance to the model. And basically that would be because if you're already in drought or already in a severe drought, then you can't really go past that. And if you're already not in a drought, then you can't ameliorate. So it makes sense that that would be an important variable. And then that was followed by the INSO phase and the location information and then the MJO. Looking at this a little bit differently with the precision recall curve. So the precision is basically saying, did we predict the positive case when it occurred? And then the sensitivity is looking at when we predicted the positive case, did it really occur or did we overpredict? And so you want both of these scores to be maximized. But looking at this, it looks like it's doing better with flash amelioration. It's more likely to predict the flash amelioration events than the flash drought events. So we still have a lot of work that we can do to improve this. The first thing that comes to mind is the lag period here. So we're using 5 weeks right now, but there may be a stronger correlation at a different lag period with the MJO. And also we can break this down into more of a regional analysis and determine which regions are affected by specific phases. We know that the MJO affects different regions differently, and then feeding more information in about which region you're in might help the model capture those effects instead of trying to look nationally. And then we also want to look at maybe trying out a different indicator here. So using the US Drought Monitor, as other people have mentioned, both in this session and earlier in the workshop, you're going to automatically have some lag there of at least a week. And then the drought monitor is sort of designed to be more resistant to rapid change. So for something like flash drought, we might want to look at a different indicator here. So we'll be testing all of that out. And I'm not writing off the MJO's impacts yet. I think there's just more breakdown to be done here. Yeah, so with that, I can take any questions that you might have.
So I think we have time for one question, if there's one in the room or online. All righty. So I think, oh, we got one coming up. Yeah.
Sorry, I know the organizers are looking to pinch time. Emma, as a Climate Hub network, we get to talk to our different regions and realize that ENSO has different effects in different regions. In the Northern Plains, one of my fellow researchers in the grassland world has also found that PDO signals, again, I'm an economist, apologies for those that don't believe in PDO, but the interaction of PDO and ENSO have implications for how variable vegetation is versus how consistent it is across years. So I'm curious how you're thinking about those regional influences of ENSO and if you're taking regional differences into account somehow.
Yeah, that's the next step here, to try and fold some of that information in on more of a regional basis. Because looking at this across the US, I think is sort of muddying the waters of each phase's impact. Okay.
I'm going to jump right into the kind of table discussion. Who's going to lead that after that?
Yeah, thanks, Ronnie. So first of all, great talks from all of the presenters over this last session. It was really good. And now just for the next 5 to 10 minutes or so, we're just going to open up this room to comments. And here's the question that I would like you to think about. And if you have an answer, come up to one of these microphones and answer it for us. From what you've heard in this session that was focusing on emerging research in flash drought, what do you think are the most important areas of research that we need to focus on next? That's the question. What are the most important areas of research that we need to focus on? And if you have an answer or you have an idea or a comment, come on up and share your idea.
And just clarifying, we've got the question up there, but we are going to do the table process for this just in the interest of time. So this is a free sharing.
Thanks for that. I probably could stand here and see what's on the screen behind me. Go ahead, Danelle.
I'm back.
Oh, great.
So Danelle Peck with the Climate Hubs. I've heard the idea a couple of times now, essentially about soil moisture climatologies. And I find that really intriguing because of the site-specific nature. I think what we've heard throughout these flash drought discussions is that flash drought is different depending on where you are. So of course it's going to look different depending on your soil types. So I love this notion of when we do get more soil moisture data available and in situ, taking a look at that historical climatology of that soil moisture, seeing how it under more normal circumstances, soil moisture depletes at important points, again, from an ag perspective, and then asking, looking for the anomalies where that soil moisture has depleted extra fast. Because that's when, again, our farmers and ranchers are noticing what they think of it as a flash drought. So soil moisture climatology.
Thanks, Danelle. And Marina, are you capturing this on a Slido? Are we doing that? So once we get the Slido going, you can thumbs up other people's ideas to help us get an idea of what ideas would also resonate well with you. Becky.
So I'm kind of now stuck on this idea that we don't have these null hypothesis cases. And I'm also thinking of a comment that was made, I can't remember if it was yesterday or the day before, that we don't really have in the research examples of real-time monitoring of flash drought. And so I see this as an opportunity where researchers can combine with practitioners who are doing these, real-time monitoring, and are we anticipating a flash drought and it doesn't happen? And instead of looking back on cases that have, that we already know it happened or didn't happen, how does it evolve, while we're in that situation and documenting it? So we have some more examples of those. Oh, this one did become a flash drought, or this one didn't, but the indicators were there. So
Fantastic. Thank you, Becky. Meredith, I think you're up next.
Hi, good morning. I think this fits into the research realm, but in the Southeast, we just went through a triple dip La Nina, and there was this expectation based on historical precedents that we would likely be set up for a drought, which never happened. And so again, understanding the MGO and all these teleconnections, et cetera. But what came up a couple days ago was our ability to communicate that uncertainty. We shouldn't be scared of sharing our research and our science and our predictions, but make sure that we're being really careful in how we communicate what it is and what it isn't. And so this is more of an extension of research, but I do think we could work better at how we communicate that uncertainty. And of course, always addressing what that uncertainty is. So thank you.
Thank you, Meredith. So communicating uncertainty. Any other ideas? What are some things that you've heard, or what are some of the most important research areas that you'd like to highlight? And if there aren't more, then I guess we've already have like our top three. We don't even really need to vote them up. But if anybody has any other ideas, one last chance to come on up. No? Okay. Okay. I'll wrap that up then. Can we get the second question up on the screen again? Okay, now Ronnie, I'm going to ask for your help with this again too. We're going to do a 1-2 table all exercise similar to what we did yesterday. for this second question. And the second question is barriers and opportunities to transition emerging flash drought research into action. So this is something that came up a few times yesterday, both in the plenary session and certainly in our breakout groups, was this research to operations or research to action. So if we can get into tables of hopefully even numbered people, so we've already got a group here. Can you three maybe join with those three in the back table, and then you two join? Maybe can we bring this table up here to join with the table with the Kansas folks here? And we've got a table of only two people here. Maybe you two can join with Jeff at that table. So we have 4 there. The other tables are pretty good. We've got 2 tables of 3. We can combine maybe if we need, unless you guys are moving. Are you guys moving somewhere? Okay, I was gonna put those 2 there. Maybe Mike, you look a little bit lost. Can you come and join this table of 3 right over here? And Art, can you come to this table of 3 that are over here? And if you need to take down some notes, you can. And you can do this however you want, but we want to note an opportunity and a barrier to accomplishing that, or a barrier to that opportunity. And I'll give you maybe 2 minutes to think about this for yourself, and then you're going to pair up with somebody to talk about it with your amigo. Do you have a timer? Perfect.
Just a message for the virtual attendees that there is a breakout room if you want to participate virtually. Go to the little boxes on the lower, should be lower right, and pick breakout room 1, I assume. Yes, breakout room 1.
Hello. So we got our first 2-minute session there. So if you guys want to turn to your right or left, maybe to your right, and talk amongst your group, and we'll give you another 2 minutes there, and then we'll do the table planning. Are you talking?
I think.
Yes. Maybe. That might be. I think it was like 1, 2, 3.
All right, everyone. I hear a lot of chatter, a lot of interesting conversations going, so that's great. We're going to give you another 8 minutes to kind of continue the conversation across the entire table, which is sounds like you guys were doing anyways. And then we'll come back for a plenary and we'll go from table to table to kind of report out. So think about who you want to give that report. Are really strong droughts. All right, guys. I'm going to go around to the tables now, if we can all bring attention here. And we're going to ask each table to kind of just highlight one or two of the barriers and opportunities when it comes to monitoring flash drought. And who's the speaker here? Have you guys, not to put you guys on the spot. I can. All right, here's Emma.
Hey, so we talked a lot about regional and sector specific breakdowns. So understanding what predictive tools are needed for specific sectors and specific regions. And then once you, the way to understand that is probably going to be through increased stakeholder communication with the research side of the equation and making more of those connections between people.
All right, thank you. And we're gonna just continue around the room here. Who's the?
All right, so we came up with a few things. One is that we have to better tie physical science results to impacts because they're so key with drought. We need to do better with communication. It's been a very common theme here. Again, we can do all the research we want, publish all we want, but in the end, we still need to get that, get those results in the hands of practitioners. And more importantly, listen to what the practitioners need. It always has to be an iterative process. So let's see, so that's better integration of physical science with user communities. And then also, more discussion between scientific disciplines. As we've been talking this week, flash drought impacts so many different parts of the environment, and it's important to not just think about this from a climatological perspective, but to also get land surface modelers involved, ecologists involved, the people that set policy. It's really important to get everybody together, to have a discussion on flash drought. Is that everything? All right, go.
Just a quick reminder that Marina is putting up these ideas onto the Slido. And if you would like to add your ideas or vote on other people's ideas, go ahead and put it in, either go to slido.com or you can take a picture of that QR code.
Yes, thank you. Please do.
So yeah, to build on some of the previous comments there, I guess the discussion at our table really kind of focused on what I characterized into three key themes. One being from a practitioner standpoint, being aware of all the ongoing research taking place and being able to interpret all of the research findings leading towards action. Second item of discussion would be getting decision makers to see the research being conducted will lead to action and believe in the science behind that research. And then the final thought would be make sure science is included in planning and decision making, as well as the benefits of kind of that stakeholder bottom up process when it comes to identification of any sort of research needs, as well as leading towards respective planning and actions from that point. So not having it be a top down sort of mandate, but facilitate some of that local buy-in at the front end to get stakeholder involvement from the get-go.
So we're going to reiterate everything else pretty much everyone else said, but to add, one of the barriers would definitely be understanding localized tipping points. So for specific areas, and so this could, so that would require also a knowledge of the impacts that are actually occurring. So then once you, if we have a better database for those impacts, then we can get more localized data, finding out what the precursor conditions are, and maybe being able to assist us with getting our indexes to actually see if they're capturing what they're doing, because they do capture things for large events, but then me working with other indexes, I've seen they may be overestimating in some areas, but we don't really have a database to go back and verify which times it wasn't doing what it was supposed to. And then future opportunities, just continue with collaborations through workshops so that we can understand where the state of science is. And then maybe doing more collaborations with utilizing different pieces from other people's research, such as where solar induced fluorescence index that's useful for not so useful for forest lands, but then what tool could we use for forests that would be better? And so kind of piecing together different people's research to create a more complete picture.
+1, +1, +1, +1. Everything you said, I'm gonna just highlight a couple of new things. It was brought up in our group that it's still hard to even answer that question of how we could put research into applications because we don't really have enough good case studies on that in the flash drought context. I mean, we're still struggling with what does flash drought mean in our region, much less how do we incorporate it into decision, planning, response, et cetera. And so that was, I thought, a really interesting point. We need to move forward in taking action from what we heard in these last couple of days, and hopefully in a few years coming back with some strong case studies. And the last one that's kind of a barrier for putting research and information into action is still a bit of the time delay and how quickly products are updated during a rapid onset event. The latency of data. Thank you.
We came up with a few. I don't think anybody's mentioned money yet. We need statutory funding for the NDMC. I don't know if that's quite the right phrase, but we need money for the NDMC, a la NIDIS, as it were. Barrier that I think, and it's my hobby horse, is we got to get over our obsession with this definition of flash drought. We're not going to get a definition of flash drought. If you're a decision maker, or if you're interested in impacts, or if you're a research scientist looking at fluxes in the states, and you come up with the perfect population of flash droughts, they're all going to be different flash droughts. It's not going to be the same population. Other barriers, or barriers that I guess we're working on. We thought that machine learning may be still yet immature for flash drought analyses, given the mix of drivers for various flash droughts in various environments. This is apparently has also come up in the drought forum. Yes, and the idea of mature versus research products, and how do we distinguish between them? We need to direct stakeholders to mature products, and researchers, you know where the research products are. And the best places to do that may be on state level pages rather than federal pages, or on sector specific pages. I think that's what I have. Yes.
We came back to the need for an operational framework. Number one, we have a plethora of great products that we've seen this week that really need that space to be transitioned. We don't have a clear pathway for transition. And then we have challenges of accessibility and usability. And when there are issues, how are they getting fixed and how quickly? And also that operational framework, we're sitting in between, Jeff said, as we're sitting in between the weather space and the climate space. How do flash drought watches get issued, and who does that? And then who's watching, who's monitoring as that situation is evolving?
We came up with a lot of the same ideas. Mostly we talked about the fact that none of us trust those in some of those models in our area, the Southeast, or in other areas. One size fits all does not work with flash drought. And so I think it's an opportunity for regional climate centers and groups like that to focus more on their own areas, to look at what causes flash drought in their areas, rather than trying to find one size fits all for the country. The other thing we talked about was impacts, and how numbers don't really help. We need to know how to communicate what the impacts of that flash drought are going to be on different communities, whether it's ecological or agriculture or whatever. And we didn't really hear a lot about that today. And so that, I think, is a real opportunity for us in the future.
All right, and Kelsey, we're going to turn it over to you if you want to summarize your top 2 points there for barriers and opportunities.
Yes, so we discussed a lot of similar things to what other tables have mentioned. One of the key barriers, as someone else mentioned, was the lack of real-time data to improve to improve predictive capacity. That lag time is a big barrier to push research forward. Another barrier was, as someone else mentioned, finding the best ways to communicate this information to the people who can use it, knowing that journal articles are not necessarily the best way to make that communication. And as a related note, the lack of funding for that communications and research to action piece. A lot of times the researchers are doing their part of the work, but then there's no one on staff to take that to the next level and through workshops or webinars or whatever pieces to bring that research to action.
Okay, so thank you very much, Kelsey. We have a 20-minute break, so if you guys want to go out and enjoy some snacks, and then we'll come back and go over the top 3 Slidos. Thank you, guys.
Well, first of all, for a while, the last one was opposite.
Good morning again, everyone. If you'll start making your way back from break, please come back to the plenary session. Virtual attendees, welcome back as well. We'll get started just shortly. All right, we're going to start with just a couple of announcements and move toward the session where we're wrapping things up. First of all, as you can see on the slides or the presentation screens behind me, we wanted to make sure everyone was aware of the annual Natural Hazards Workshop coming up in July. We feel like there's a great overlap between the folks attending this workshop and this workshop coming up in July. So do consider going online and getting some more information on the Natural Hazards Center's workshop, and we will support them in their efforts because we know it's going to help our efforts with flash drought as well. Evaluations. We have evaluations on your tables. You can start to take a look at those and let us know how we did with organizing this workshop, generally in terms of the structure of the workshop. And of course, we'll take any comments on content as well. The evaluations will also probably be available in an electronic form sent to you an email after we depart from this particular area, but these forms will be helpful to us right away. Resources. There will be a tab, I think it's going to be called Resources tab on the workshop website that you originally went to register for to come here. That tab will have probably some more of the information from things like the Tools Cafe, including the links to the tools, so you can share those with folks when you get back home. A reminder that the plenary sessions are recorded, have been recorded, and we will be putting together a workshop recap that will be available on drought.gov. So it'll be, again, if you missed a particular presentation, had questions, couldn't reach the original presenters, you can just go back and replay the recording. It'll be time hacked, so you can skip to the ones that you are interested in reviewing. And we hope that should be available within a couple of weeks. And I just wanted to double check, do we have Molly or Kelsey with us for the virtual moderator?
Hello, it's Molly now.
Thank you, Molly. Many, many thanks to you and Kelsey today. Thanks. Let's move on now with Meredith. Meredith will walk us through our final exercise with the incredible use of the flip charts.
Yes, yes. Okay, we have just spent 2.5 days with a lot of similar questions, which is, you know, what more is needed? We, you know, just going through our schedule of what we covered. We asked practitioners what information will help you do your job for response and planning. We broke out in breakout groups at the regional level. You know, do we have the information we need for early warning system? What more could we do? And then we just had similar questions for the research community. You know, well, what's next? You know, what can we do? And so we have a lot that's been captured. A lot of it was in 2020 discussions and synthesized in that report. But I think we've gone a little bit deeper and expanded a little bit more. And again, our NIDIS team is going to help to capture all of that came out of here. But what we really want to spend this last hour on is just, we have so much incredible expertise in this room. You all have your own individual networks, you have your own background, you have your own perspectives. I mean, such diversity in this room. And we really need to use it in this last hour to help us move forward. Because it's one thing for us to just say, oh, yes, we need to increase the lead time of flash drought, but what does that really look like in practice? How do we make this happen as a community? Who's going to do it? Who's going to fund it? Who's going to implement it? Who's going to advocate for it? And so what we're planning on doing right now is to just, we're going to have some stations along the lines of these. Actually, could you put up the next slide, please? That would be great. Thank you. Along these topics, there's going to be one station on monitoring. Who is monitoring? Thank you. That's Marina over there. Don't worry, you don't have to remember where anybody is. One on prediction, which is Amanda. One on response, flash drought. Again, we're talking flash drought, not drought writ large. So keep that in mind. Sylvia, we have Gretel doing planning. And then we have Britt, network building and coordination, and Joel doing characterizing flash drought. These were the categories identified for priority actions in the 2020 report. And we just want to continue. It sounds like a lot of what we identified as gaps and needs and moving forward still exist. And we've added to that list. And what we want to do now is kind of get you guys moving for the last hour and walk around. And so, for example, when we talk about, how do we tie indicators to impacts? That's great. Let's put that on the list. It's on the list. What does that really mean? Do you guys have any ideas? I mean, are there pilots? Should we be focusing on pilots? Should we engage a certain entity that's not in the room, certain professional association, a sector? What are some, from your experience, how can we move the needle so that if we come back here in 3 years and we do my bingo card, which I promise you all have, that we can also be able to point to, wow, we really made some change in what we said we were going to do. And so with that in mind, what I'm going to do is I am just going to point to a table, right? We're back in kindergarten. And I'm going to say, could you please go over to, and we'll do a little test case. So this with Elliot and that group, Danielle, why don't you go right behind you to Gretel? And then I'm going to start assigning other people to go to just tables and just kind of look. I mean, the tables are from, and you're going to stay there for about 8 minutes. And you're just going to brainstorm and just, you can start writing down things. And then we have our helpful assistants there, our Vanner Whites, who are also going to be helping maybe capture just anything like that. This is a brain dump here. We want to get a little meat on the bone of what's next. It's not going to be exhaustive, but this is our way to move forward. And so, in fact, I'm not even going to assign you because we're not in kindergarten. I would really like for all of you to stand up and kind of, you can do this. I know you can do this, is just distribute yourself relatively evenly around these tables. I don't know if you guys, and then just, I'm going to stay at that table until you hear me say move. And then you're just going to shift to the next one. So this way, everybody has a chance to comment and think about what's next for response and planning. And even if you're not working in response and planning, your perspective working in monitoring and research, et cetera, is really important. So we would love for everybody to just walk and talk. So with that, is there any questions of what's to expect? You're going to stay at a station for a few minutes. I'll say move, and then you're just going to move clockwise. There we go.
Meredith,
Yes.
I just want to make a brief comment for the virtual audience. I think
Oh, thank
Molly
you.
will be working with you guys on a Jamboard exercise.
Yes, and I'm actually was waiting. We need to have a breakout room established on Zoom,
Correct. Yep.
which we don't have. So
Yep.
there
they're
we
on-
go.
they're
We're on it. Okay. All right.
Great. Enjoy, you guys.
Okay, thank you. Thank you so much. Yeah, those of you working in the research communities, do you know like some NSF programs, some DOE programs that we can go ahead and take the outcomes from this to here or there? So we want to know your Rolodex, your networks of how we can, I think Mark made this comment the other day, I know most of the people in this room, how we can start to increasingly expand our flash drought community. So with that, everybody up and nobody sneak out. No, just kidding. You're fine, but I will take photos. Thank you. Yeah, let's go. Okay, that's a wrap. Thank you to all of my kindergarten students. 1, 2, 3, eyes on me. Do you guys know how to do that? This is what they do in kindergarten. I say 1, 2, 3, eyes on me. And you repeat 1, 2, eyes on you. Ready? 1, 2, 3, eyes on me. Yep, that works in kindergarten much better than at the National Flash Drought Workshop. Could everybody please come and take your seats? Thank you so much to the facilitators at each table. I really appreciate it. There's a lot written there. It's a little overwhelming. Okay, am I passing this off to Sylvia? Awesome.
I almost don't know what to say, other than well done. I think we can all give ourselves a round of applause. I'll pat myself and Marina a little bit on the back because we made up a 20-minute deficit there. And we're going to be able to get everybody out of here actually a couple minutes ahead of time. But in terms of reflections, I just want to thank you for coming here, for being a part of the workshop. The NIDIS team will be working hard with pulling together all of your inputs and the information shared and the ideas. You will be seeing reports, you'll be seeing postings on drought.gov, even in the short term, even if it's just the recordings that you want to go back and take a listen to. So thank you for your time, your efforts, and have a safe trip back home, wherever that may be. Bye.
And thank you to our virtual audience and in particular our virtual moderators who did such a great job. Thank you to the UCAR team getting us through all of this together. Thank you, I will say, to the fabulous NIDIS team for a job well done. And I'll stop talking now.
There's a cell phone here.
Probably mine.
There's a power charger on the back. You got it. No.